Hello guys, welcome back. So the question above, we were told to find the shear force and bending moment of the diagram. So at point A we have a point load, at C we have another point load, at D we have a point load, and at E we have a point load. Between A and B we have a UDL, uniformly distributed load. So we are going to be calculating for the shear force first. So first we deal with Newton. So at every point load we are going to be calculating the shear force after the point load and before the point load. So we are going to start with A. So shear force before A, shear force will be equal to 0. So now shear force after A, that is after A, the shear force will be equal to, we have a force RA at point A, which is 22.5. So at A, the shear force will be equal to 22.5 Newton. So B is not at point B. We don't have a point load. So what we are going to be doing for B, we are going to be looking for the shear force at B. But for others, we have point load there, we have point load there, we have point load, then we have point load there. We are going to be doing for before A, shear force before A, and shear force after A. So at this point B, there's no point load. We only have a UDL. So how to calculate the shear force at this point B? We are going to be looking for at B. So we are going to say at B. So shear force at B will now be equal to, this is a UDL, this is Newton per meter, but for force we work with Newton. So this is Newton per meter. We have to convert this force, we have to convert this Newton per meter to meter. In order to convert it, we are going to be multiplying this 15 by the distance from this place to this place, that is 2. So the force here will be 15 times 2. So this is acting downward, so that will be negative, and we have 22.5 Newton up here. So shear force at B now will now be equal to 22.5 minus the force here, which is 15 times 2. 15 times 2, which will now be equal to minus 7.5 Newton. So at C, we have a point load. So at C now, we'll be doing shear force before C and shear force after C. So before C, shear force before C will remain the same. Q will be equal to, it will remain the same as minus 7.5. It will not change. Minus 7.5 Newton. So after C, shear force will change now. So after C, let me go back to the diagram. At point C, we have a 20 Newton point load. So after C now, we'll now be having something like this, minus 7.5 minus 20, which will now be equal to minus 27.5 Newton. So at point D, this is a point load. So we are also going to be doing shear force before D and after D. So before D will remain the same as minus 27.5. So after D, now this will change. So after D, when we come back here, we have 47.5. So we are going to be adding 47.5 with the remaining force. So this will be minus 27.5 plus 47.5, which is equal to what? 20. So before E, this is E. At E, we have a point load, so we are going to be doing shear force before E and after E. So before E, our shear force remains the same, Q equal to 20 Newton. But after E, our shear force will not change now. At point E, we have 20 Newton. So this is acting downward. That will be minus. So that will be 20 minus 20. This 20 here, then minus the point load here, which is 20. So this will give us 0. So we are done with the shear forces. Okay, this is Newton. So for bending moment, now we have to calculate for the bending moment of the diagram. For bending moment, so if we go back to the diagram, to calculate the bending moment of this diagram, from the word moment, we know moment will be force times perpendicular distance. So at every point, we are going to just be looking for at point A, at B, at C, at D, at E. For bending moment, we don't do for after A, we don't do for after B. So at point A, we are going to calculate for the shear force, for the moment, sorry. So at A, our bending moment MA will be equal to 0. That's at point A. So at B, let's move close to the diagram now. At point B, we have B here. This is B. So we need to calculate the bending moment at point B. So we know moment is force times distance. So we have a force here and we have another force here. This is a UDL. The force of this UDL will be acting at the middle. Then the middle, let's say the middle is here. So that will be 2 divided by 2, which is 1. So from this point to this point, that is where the UDL will be acting, which is 1 meter. So this is in Newton per meter. We have to convert it to force, then multiply it by the distance of this place to this place. That's the force times distance. So at point B, let's start at point B. Our bending moment now will be equal to 22.5, which is the force at A, times the distance to B, which is 2. 22.5 times 2 minus, we have our UDL here. The force of this UDL is 15 times 2. That's just the force, 15 times 2 in Newton. Then we multiply it with the distance. The distance of the UDL to B is 1. From here to here is 1. So times 1, which will now be getting 15, which is 15 Newton per meter. So at C, let's go back to the diagram. At C, this is C. The distance from here to point C is 3 meters. So at C, our bending moment at C will be equal to 22.5. That is the force at A times the distance to point C, which is 3 meters, minus, let's go back to the diagram. This is 15. So the force of this UDL is 15 times 2, which is 30. So 30 will be acting from this point to point C here. So we have 1 meter here plus another 1 meter, which is 2. So we'll be having minus 15 times 2 multiplied by 2, which will give us 7.5 Newton per meter. So that's our at point C. That's the bending moment at point C. So move to point D. At D, bending moment at point D. Let's go back to the diagram. At point D, this is D. So at point D, we are having 3 forces acting now. We have at RA here, we have C, we have a point load, and at B, between A and B, we have a UDL. So at C, we'll be having 22.5 times the distance from here to here, which to D, which is 3, then times 15 times 2, that's the force acting at the middle, plus times 1 plus 1 plus 1, which is 3 also. So it's 22.5 times 4 minus 30, which is the force here, times 1 plus 1 plus 1, which is 3, then minus 20 times 1, the distance from C to D. So we'll be having something like this here. We'll be having at D, A, B, C, this is C, sorry, this is D. So bending moment at D will be 22.5 times 4 minus 15 times 2, which is the force on that UDL, then times 3, then minus 20 times 1, which will now be equal to minus 20 Newton per meter. This is our bending moment at D. So at E, let's go back to the diagram. This is E. So at C, we will have 1, 2, 3, 4. So we have 4 forces that we are going to be working out in respect to E. So at point E, the force here will be 22.5. The bending moment will be 22.5 times the distance from this place to E, which is 2 plus 1 plus 1 plus 1, which is 5. So 22.5 times 5 minus the force here is 30. 15 times 2 is 30. 30 times 1 plus 1 plus 1 plus 1, which is 4. That's 30 times 4. Then minus 20 times 2. Then plus 47.5 times 1. So that will be the force, the bending moment at E. So bending moment at E will be equal to 22.5, which is the force times the distance from A to E, which is 5. Then minus 15 times 2, which is 30, times 4. Then minus 20 times 2. Then plus 47.5 times 1, which will give us 0 Newton per meter. So we start at 0, we end at 0. And for shear force, we start at 0, we end at 0. Thank you.